Hello everyone, this is lecture 10 of course BE544. In the previous lecture, we have discussed the meaning of classification and how to build a model and handle it, aiming to fit the current data or any data and generalize to the testing data and report high performance metrics. Some of the metrics that were reported were accuracy, recall, and precision. So in this lecture, we are going to understand the meaning of each metric and how to calculate it. So classification performance metrics are crucial for evaluating the effectiveness of a classification model, as they help to determine how well the model can differentiate between different classes, and the metrics provide insights into various aspects of the model's behavior. To calculate the classification matrix, you need something called a confusion matrix. A confusion matrix is a tool used to evaluate the performance of a classification model by summarizing the correct and incorrect predictions in a tabular format. As you see in the right figure, this is a tabular format of a confusion matrix that combines between four components, namely true positive, false negative, and true negative. So, what are the meaning of each component of those? In the beginning, the confusion matrix has a shape of n by n, and n reflects the number of classes. So, if we have two classes, so the shape of the confusion matrix will be 2 by 2. And if we have four classes, as in our case, the confusion matrix will be 4 by 4. And we saw that in the previous examples. We got a confusion matrix that was 4 by 4. And if you noticed, you will find that the rows reflects the actual or the prediction, and the columns will be the opposite of it. So in our case, the column reflects the actual and the rows reflects the predictions. You can swap between them, but of course, the confusion matrix will be different. So, what is the meaning of each component and how to build each component in the confusion matrix accurately? When you see a true positive, this means that the true positives reflect the cases where the model's prediction matches the actual positive class. For example, if we have a medical diagnosis system, a true positive would be when a patient with a disease is correctly diagnosed as having that disease. And the true negative is the opposite. True negatives reflect the cases where the model's prediction matches the actual negative class. Using the same medical system, a true negative would be when a healthy patient is correctly diagnosed as not having the disease. And false positive or type 1 error, these are the cases where the model predicts the positive class incorrectly. Talking medically, a false positive would be when a healthy patient is incorrectly diagnosed as having the disease. And false negative or type 2 error, these are the cases where the model predicts the negative class incorrectly. And in our example, a false negative would be when a patient with a disease is incorrectly diagnosed as healthy. So now we understand the meaning behind each component of those. Now how to put the components correctly in the confusion matrix. After setting the rows and the columns to be actual or predicted, you need to define each column to be positive, negative, or which class are you using. If you are using 4 classes, as in our example, the columns will be benign, invasive, and so on. And the same for rows. Here, in that example, the first column is the positive or true, the second column is the negative or false, and the same for the rows, positive and then negative. So, if the confusion matrix is empty and we need to translate the rows and the columns in a component, we simply check the intersection between the columns and row, which reflects the cell itself. So for example, if we are here, this means that the actual is positive and the prediction is positive, and simply this will be positive. To determine between true and false, you simply check if the actual and prediction match or not. There is a match, so this will be true. What about here? This is negative actual and positive prediction, so there is no match and this will be false. And positive here reflects the prediction. So if we are here, simply you say it's negative. And to determine between true and false, you check that column and that row. You see that there is no match, so it will be false. False negative. Here, negative and negative, so it will be true negative. So simply positive or negative is the reflection of the prediction. True or false, whether there is a match or not. Based on the confusion matrix, you can build a set of confusion metrics such as accuracy and recall. So the accuracy is the overall correctness of the model, and it's calculated using true positive plus true negative over the whole confusion matrix. Precision, this is the proportion of positive predictions that are correct, and it can be calculated using true positive over true positive and false positive. Recall and its call sensitivity or true positive rate, it's the proportion of actual positives that are correctly identified, and it's true positive over true positive and false negative. So simply from the confusion matrix and the definition, you get the actual positives and you get the correctly identified, and divide both of them, you will get the sensitivity. It will be true positive over true positive plus false negative. And specificity or true negative rate is the proportion of actual negatives that are correctly identified. So the actual negatives that are correctly identified, you divide true negative over true negative plus false positive. F1 score is the harmonic mean of precision and recall, providing a single metric that balances between them. So you will find the precision and recall in the numerator. There is a multiplication, and in the denominator you will find addition, and you multiply here by 2. False positive rate, it's the opposite of specificity. So it's a proportion of actual negatives that are incorrectly identified as positive. So if you went to the specificity and we were dividing true negative, now we are dividing false positive over the summation of that column. And false negative rate is the opposite of recall. It reflects the proportion of actual positives that are incorrectly identified as negative. So here we will divide false negative over false negative and true positive. Last but not least, Matthews correlation coefficient or MCC. It's a measure of the quality of binary classification considering all 4 components of the confusion matrix. As you see, it combines the different components of the confusion matrix in a single metric. As mentioned, if you swapped between the actual, predicted, or the classes themselves, you will get a different confusion matrix. So for example here, the prediction in the columns and the actual in the rows, and we swapped also between both classes. Here is negative, here is positive. So you'll find that the confusion matrix components are different. So simply to reach that field or that cell, you make an intersection and simply you say it will be positive because the prediction is positive. And to check there is a match or not, you check there is here negative and here positive, so there is no match, it will be false, false positive. What about that field? Simply prediction is true, so it will be positive, false and true, it will be false, false positive. What about if we need to reflect the meaning of that on a 4x4 matrix? We will follow the same concept of 2 by 2 confusion matrix and apply that on the 4 by 4 or n by n confusion matrix. This is 4 by 4 confusion matrix where the rows are actual and columns are prediction, and to understand any field of them, you simply make the intersection, check if there is a match or not, to consider false negative or false positive, or the difference between false and true. So let's begin with the normal class. To get the 4 components of the normal class, we start by true positive. True positive means there is a match in the class, and that class happens in the prediction and actual, so it will be 50. False positive means it's predicted to be that class which is positive, and false means there is a mismatch between actual and predicted. So this is the prediction of being that class or positive. We took that for the true positive, so the remaining will be false positive. False negative. Negative means it's predicted to be not that class, and there is a mismatch between actual and predicted. So this is a normal that got incorrect predictions and there is a mismatch. So this will be the false negative. So now we have false positive, false negative, true positive. What about the true negative? The true negative will be any other cells. So this will be the true negative. Let's get another example, the benign class. So let's start by true positive. True positive means there is a match between prediction and actual, so it will be 45. False positive. False positive mean we select the column that is correctly predicted as benign. There is a mismatch between the actual and prediction, so it will be 2 plus 2 plus 1. For the false negative, this means it's incorrectly predicted and there is a mismatch between the actual and the prediction, so we select that row and these cells because they are incorrectly predicted to be benign. What about the true negative? It will be the remaining of all other cells. 50 plus 1 plus 0 plus 3 plus 40 plus 1 plus 2 plus 7 plus 51. You will do the same for other classes. So after doing that, you will obtain 16 components. Each reflects a specific meaning for a specific class. So how to report the metrics? How to say that I got a portion of accuracy, some number of sensitivity, and so on. You simply have two options. Whether you report the accuracy of each class, precision of each class, sensitivity for each class, and so on, by dealing with each class separately of the others, or you can create an overall metric on the system or the pipeline that you are dealing with. So to create an overall metric such as overall sensitivity, overall precision of the system, you have three options: weighted, macro, and micro. The weighted metric considers the number of instances of each class when computing the overall metric. So this means that the classes with more instances will have higher influence on the final metric, because you are simply calculating the metric for each class and multiplying it by a weight. This weight is calculated simply by dividing the number of instances for that class on the number of the instances in the dataset. So if you have imbalanced dataset, the classes with higher number of instances will get higher influence on that metric. Macrometric. It calculates the metric independently of each class and then average the results. This means you are treating all classes equally regardless of their size. So you will calculate the metrics and divide it by the number of classes. So it can look similar to the weighted average formula, but instead of getting a weight, you are setting the weight to be 1 to 4. You are giving the same weight for all classes. Micrometric. It aggregates the contribution of the classes to compute the overall metric, and this metric treats every instance equally, irrespective of the class it belongs to. And the formula is shown here. You are simply calculating all of the true positives, all of the false positives, all of the true negative, all of the false negative, the summation of the 4 components, and based on that summation, you can calculate the metric after that. To understand how to calculate the 3 approaches, we can get an example. This is the confusion matrix that we saw earlier, and we need to calculate the recall or sensitivity for the 3 approaches, macro, micro, and weighted. So let's start with the macro. In the macro, you are calculating each metric for each class independently and then divide by 4. So you will calculate the recall for the normal class, benign, in situ, and invasive, and then divide by 4 to get the result. For example, the recall for the normal, it's a true positive divided by true positive and false negative. And as you see here, this is a summary of the 4 components for each class. To get true positive for the normal class, it's 50, and false negative will be 5. So it will be 50 divided by 50 plus 5. Benign will be 45 divided by 45 plus 10, and so on. So the overall metric or the overall macro metric will be 86%. What about the micro? For the micro, you are summing each component and then inject it in the equation. So for the true positive, you are summing all of the true positives and all of the false negatives, divide them together, and you get the result about 86.5%. For the weighted, you calculate the same similar to macro, but instead of dividing by 4, you are multiplying each metric by a weight. To get the weights of each class, you simply create a column here, sum all of the actuals for each class. For example, this is the actual normal, so 50 plus 2 plus 1 plus 2 will be 55. For the benign, 3 plus 45 plus 5 plus 2 will be also 55. For in situ, it will be 50. For invasive, will be 55. You calculated all of them. To get the denominator for the weight, you sum all of these 4 values and you get a value here. The weight for the normal will be 55 divided by the summation. The weight for the benign will be 55 divided by the summation, and so on. So you are multiplying the weight of the normal multiplied by its recall, the same for benign, the weight and corresponding recall, and the same for others. Finally, you get a recall of 86.5%. Now you understand the meaning of each component, how to calculate the metrics using 3 approaches if you have multi-class classification. But if you have binary classification, you just use a traditional approach. You will not need macro, micro, or weighted, because you will get only 4 components. But in multi-class classification, you will get more than 4 components, 4 components for each class. So you will need to apply macro, micro, or weighted to get an overall performance of the system. So how to do that programmatically? We simply create the balanced classes confusion matrix, as you see here, similar to the example, and then converted it to a NumPy array, and the NumPy package is imported at the top of the code. Then to calculate the 4 components, the true positive will be a vector that reflects the diagonal. It will be 50, 45, 40, 51 as true for each class. False positive will be the summation of each column without the true positive. So we will sum the confusion matrix axis of 0. This means we are summing here 3 plus 1 plus 0 and ignoring the true positive that reflects that class. So the first will be 5, the second will be 5, and so on. The false negative will be similar, but for axis of 1. This means we are summing in the direction. So it will be 5, 10, 10, and so on. And you are not summing 50, 45, 40, and 51 because you are subtracting the true positive from it. And each of those will be a vector. This is a vector. This is a vector subtracted from a vector that will result in a vector. So each of them will be a vector of 4 values. Each reflects a class. True negative will be the remaining of the confusion matrix. So simply you sum the confusion matrix and subtract the summation of all other components, as we did during the discussion. After doing that, we will get 4 vectors. These vectors will look like these vectors that we used in our example. We printed the 4 components, then we started to calculate the matrix for each of them. Simply to get the macro, you are calculating each metric independently and then calculating the average, or simply you can divide by 4. And 4 here reflects the number of classes. So instead of setting each time the number of classes, you simply take the average and it will calculate the number of classes or the average number depending on the number of elements in each vector without any manual handling. For the micro, you are summing each component and injecting that in the formula. So you are summing true positive, and false negative, and this will be the precision. Summing true positive and false negative, this will be the recall, and so on. For the weighted average, you will need the weights. So we will get the column we calculated here by simply summing with the axis of 1. So we will sum depending on each row like that. Then to get the weights, you divide the sum of each row or each actual class by the summation of the whole confusion matrix. Now you have the weights. You can simply now, instead of calculating the mean, you calculate the sum multiplied by the weights. So a vector by a vector, this is a vector multiplied by a vector, it will result a vector because we are multiplying pairwise. Then we will sum the whole vector to get a single value. After that, we printed micro, macro, and weighted matrix. And when we execute the code, these are the corresponding matrix plus the weights and samples, summation. And this is the tabular format of it. As you notice, the matrix are close together. For example, the recall, all of them are around 86. This happened because we are dealing with balanced dataset. What about if we have imbalanced dataset? Imbalanced dataset means that some classes has higher number of instances over other classes. So for example, the benign here has the higher number of instances. If we summed that row, it will be more than 130, which is 135, which is higher than other classes. And this will have an influence on the matrix. So if you are dealing with all of them equally, you will get a recall, for example, about 78. But if you are dealing as weighted, it will be 82. And if you are using micro, it will be also 82. And the same for other classes. And to say that there is a significant gap and there is a noticeable difference between macro, micro, and weighted, you can simply inject, instead of 120, you can set it to 500. This means there is a large gap between the benign and other classes. You can see the time that there is a huge gap between the metrics. So when to use each of them? There is a comparison table between the 3 metrics, the description of them, and the recommendation of using each of them. And for simplicity, if you have balanced dataset, you can use micro or macro. And if you are using imbalanced dataset, you can use weighted or micro. As you see here, the micro and weighted for the imbalanced dataset looks similar in most of the metrics, such as here they are close, and here they are close. And for the balanced dataset in the first example, we said macro and micro, and for binary classification you can use micro and weighted. And as mentioned, for the binary classification you will get only 4 components if you are dealing it as an overall 2x2 matrix, so you may not need to calculate the weighted, micro or macro, and you are just simply injecting the 4 components in the equations and calculating them. But for multi-class classification, you are encouraged to use the macro and weighted with the reflection of the previous slide, which is here, to differentiate if this dataset is balanced or not. This recommendation can help you judge the performance of the system and check its generalizability. In our examples, we dealt with simple CNN models. We applied dropout, data augmentation, trying to increase and enhance the performance of the system. There is another approach after the simple CNN, or creating a CNN from scratch. This is called using a pre-trained model or transfer learning. So pre-trained models are models that were previously trained on large datasets such as ImageNet, and ImageNet here is a large dataset, and then you can fine-tune that pre-trained model on a specific task or the task in hand. One of the primary benefits of using pre-trained models is the ability of the generalizability. So these models have the ability to generalize well across different tasks. For instance, models like VGG16, ResNet50, and Inception version 3, these models were trained on millions of images, as mentioned in the ImageNet dataset, and this model learned to recognize many features such as edges, texture, shapes, and objects. So you can use that pre-trained, inject it into your dataset, and start to fine-tune it. So by using pre-trained model, you can reduce the computational cost and time required to train deep networks from scratch, because the initial layers already contain variable learned representations. So you can modify only the final layers to suit the new task in hand and retrain or fine-tune the model on the new dataset. And to do that, you can simply freeze these initial layers and only keep the last or the final layers unfrozen. So we can say the early layers of the pre-trained model, which capture the low-level feature, are typically trained, while the later or the final layers are adjusted to learn task-specific features. There are many models, as mentioned: VGG16, ResNet50, Inception version 3, MobileNet, and many others. One of those are MobileNet version 2. You can find also MobileNet. There is also VGG16, and if you notice, each of them has a specific architecture and contribution that led that model to be widely used in many applications. And all of these pre-trained models are available in Keras or TensorFlow in something called Keras Applications. So if you went to that website, you will find a long list of available models that you can use. For example, here, Exception, VGG16, VGG19, and ResNet50. You will find also its size, the number of parameters, the depth, and other factors. For example, VGG16 has more than 130 million parameters, while ResNet50 has around 25 million parameters. So you have a variety, and it doesn't guarantee that all models will work well on your dataset. So you need to select the best of them that neither underfit or overfit. So you can start simply by the models with less number of parameters and increase the complexity based on the results, if there is overfitting or underfitting. As mentioned in the previous classes, on the ways of overcoming the overfitting and underfitting. Based on that, you can select a simpler model or a more complex model. So how to write a code using transfer learning and applying pre-trained models? Based on the confusion matrix and metrics that we calculated, we encapsulated all of them in a function that finally returned a dictionary that includes the three approaches, weighted, macro, and micro, and it accepted the confusion matrix, so we need to pass a confusion matrix and get a dictionary. After that, we defined the configurations, and it checked if there is a split or not. If there is no split, it will start to split the data set, and now we are dealing with level 0 with a size of 256 by 256. Then we created the generators, train, validation, and testing. And earlier we created a simple model in a function. Now we are replacing that with a pre-trained model, and namely here it's MobileNet version 2. MobileNet version 2 can be accessed as mentioned from Keras Applications. So we are here importing all of the models from the applications model in Keras and TensorFlow. And you simply write ImageNet here as the pre-trained weights, which is default also by ImageNet. You can ignore that and set it to none, and in that case it will be randomly initiated. You are giving the input shape, and you are setting include top to be false, as we have a specific shape of the input layer, which is 256 by 256. Now we have a base model, and we need to freeze that model, or at least freeze a set of layers at the beginning of that model. So we are looping on each layer in the base model and freezing it by simply setting the trainable to be false. So if you have any layer and set layer or the name of the layer or the object dot trainable to false, this means it will not update the weights of it during the training process. After that, we got the base model, applied a set of trainable models at the end of it. So these layers will be only updated. I'm talking about dense layers because dropout and the global average are not trainable. So after the training, these are the only layers that will be trained. And finally, we applied dense layer of 4 classes with a softmax activation function. The rest of the code is similar to the previous code that we created in it in a simple CNN. Here we compiled with Adam optimizer, apply the metrics and loss function to be categorical cross entropy, because here we defined the class mode to be categorical as we are dealing with one hot encoding. Then we started to train and fit the model with the same configuration. Then we loaded the best model or the best checkpoint, then printed the metric for each category, training, validation, and testing, plotted the learning curves, and finally calculated the confusion matrix. In the previous code, we stopped at that point, but here, because we created a function that calculates the metrics, we applied the confusion matrix that we calculated from here to get the results, and for each result, we are printing the values. After training and executing the code, we can notice that these are the results: weighted, macro, and micro. We notice that the recall is about 84, 84, 84. This is because we are dealing with balanced set. You can try the same code with imbalanced dataset, and you can notice there is a difference between the 3 approaches. So in this lecture, we have dealt with the different performance metrics. We got 3 approaches: macro, micro, and weighted. We calculated different metrics and encapsulated how to calculate them in a function. And then we dealt with something called pre-trained model or transfer learning, and the concept behind it. There is a model that is initially trained on a larger sets such as ImageNet, and then you are transfer its learning by simply freezing the trained layers as we saw in the example, and then engage it or added some layers at the end of it, and you are training these layers to fit the new data set.